the alcohols. You remember those well. This semester, chapter 16, we did the zinc amalgam reduction, the Clemmensen reduction of phenyl ketones to turn the acyl meta para-directing substituent into alkyl auto-para-directing. Chapter 17.6, we did hydration. That's very recently. We did hemiacetal formation, alcohol, acetal formation with acid, thioacetal, amines, and so on. And here's Wittig. And all the way down here, that's what we just did a second ago. Here is the Baeyer-Villiger oxidation. But this continues. Okay, so chapter 18, there's 1, 2, 3, 4, 5, 6, 7. And there's a second part to this. This is the biggest roadmap in the book. All the others are one page. This is a two-pager because it keeps on going all around. So it gives you the functional group at a glance. And that could be very useful. So here's the alternative, namely all the arrows going inward, namely a preparation of this functional group. And again, chapter 8, we start with alcohols being oxidized with chromium-6. Chapter 12, ozonolysis. That's another way of making carbonyls. Chapter 13, alkyne hydration, and so on. Okay, so they're all there. They're going in order. The section number is given, and you can organize your thought. And you keep going back to this as we add new chemistry. So you should use this or your own system of tabulating these things. I recommend that you tear out these pages and put them in your pocket and read them as you're sitting in the bus or do whatever, sitting on the toilet if necessary. And by all means, mutilate my book. I don't care. And which reminds me, one of you told me that in the dorm room they have a picture of me that they throw dots at. Okay? Whatever turns you on, I don't care, as long as you learn something. Okay? So keep that in mind. Okay. So logically now, after discussing the carbonyl reactivity, we'll go to the other center of reactivity, which is the alpha position. And we briefly mentioned this already in the introduction to carbonyl compounds. This is a special position, and you already know why, because it's actually allylic. It's not a normal allyl, it's not a carbon-based allylic system, it's an oxygen-based allylic system, but that alone imparts special reactivity on that carbon. The oxygen is really the icing on the cake, because the oxygen is electron withdrawing, which makes this position particularly acidic. Okay? And so consequently, this proton is labile. And indeed, these guys are in equilibrium with their corresponding enol forms, where the proton is shifted from this carbon over to the oxygen. We've seen enols before. Those were the products that we got from hydration of alkynes, where we added HOH across a triple bond. Out came a double bond with a hydroxy. And we said repeatedly at those stages, that these are unstable with respect to tautomerization, it's called, meaning proton shifting from the oxygen to the carbon. The driving force is the strength of the carbon-oxygen double bond, which is very strong in part because it's a polar bond. And so Coulomb's law adds an extra increment of bond strength to the overlap that gives you a strong bond. Same reason why triphenylphosphine oxide is so stable. The PO bond is so strong because it has a strong polar component. So how do we deal with this? Well, first of all, how acidic is it? Now, actually looking at some real numbers. And you find that it's around 20. Okay? The aldehydes are a little bit more acidic than 20, around 17. They're more acidic than ketones. Why? Because aldehydes have a more reactive carbonyl function, meaning more delta plus on that carbon relative to ketones. In aldehydes, this is a hydrogen here. In ketones, this is an alkyl group. The alkyl group pushes, stabilizing the delta plus, so this piece is happier as a carbonyl. The aldehydes are less happy. And that translates into the acidity, of course. The aldehydes, the 4-methyl group, pulls more than the acyl group of a ketone. And so it's not worth much, but it's about a factor of 100. So around 17 for aldehydes, 20 for ketones. If you remember around 20, that's good, because I want you to compare this to alcohols. It's close to alcohols. Not quite, but relatively close. Alcohols are around 15, right? Water, let's call water 15, and methanol 15. They go from 15 to 18. For the tertiary alcohols, they are as high as 18. But 15 is a good, well, 15 to 18. So that's close to those. The alcohols are, a factor of 100 to 10,000 less acidic, more acidic than these. But they're in the same ballpark, maybe that's what I should say. For a CH bond, that's pretty good. Okay? We've seen a scenario for a CH bond only once before, and that was cyclopentadiene, where aromaticity made the CH bond so acidic, because you formed the cyclopentadienyl anion. But here, it's just induction and resonance. Compare this to propene, which is this molecule where this is a carbon, or propene-like. That's 40. Okay? So there's an enormous kick that you get out of the oxygen. So when you deprotonate, you get this anion, and you can write various resonance forms. I did this, that's just to this one, which is a very minor form, just to rub in the fact that the CO double bond is highly polarized. You can express this by actually completely dipolarizing it, so to speak, by moving the electron pair from here to here, and that puts a plus charge here and a negative charge here, and then plus and minus then make the double bond. But the two major ones are these two. Okay? That's the carbonyl form, where it's a carbanion, and that's the enolate form, enol oxygen anion. Which one is dominant? We learned that in chapter 2, not 1, when we did Lewis structures. When you have two non-equivalent Lewis structures, you look for electronegativity effects. Oxygen is more electronegative than carbon, so it prefers to pick up the charge. So this will be the dominant form. But that doesn't mean that there isn't a sizable amount of negative charge on this carbon. It just happens that there's more negative charge on the oxygen. And you can see this in the potential electrostatic potential map, which indicates charge distribution of acetone enolate, and you see that it's quite red on this carbon, okay? Even though more red on the oxygen. Okay? So enolates you can view as oxaallyls, okay? Oxygen-bearing allylic systems by this resonance. So what do we need to completely deprotonate? Not just set up an equilibrium, acid-base equilibrium, but completely convert an aldehyde or ketone to the corresponding enolate ine. You need a base that is stronger than the corresponding enolate anion. Okay, so simple acid-base stoichiometry. Chem 1, high school. And a perfect base for this is LDA. You might have thought, let's see, we just used butyllithium. Butyllithium is a great base, and we've used butyllithium frequently to deprotonate. Well, it doesn't work. And you also know why, although it's in a different compartment of your brain. Butyllithium doesn't work because it adds to carbonyls. We know that from chapter 8. So there, the base doesn't act as a base, it actually acts as a nucleophile. And you don't want that. And the way to typically turn off the nucleophilic power of a base, or potential of a base, is to make it hindered. And that's exactly what we're doing with LDA. Lithium diisopropylamide, where the isopropyl, or 1-methyl-ethyl, according to our UPAC substituent, is big, and it makes it bulky, and so addition to the carbonyl is not observed. Rather, it acts as a base. So that's stoichiometric deprotonation, meaning that it's a quantitative conversion. No carbonyl left. Everything is enolate. Now, we will see that it often suffices to have equilibrium concentrations of enolates in your reaction mixture, because we will find reagents that will not react with the carbonyl form of the species, but will react with the enolate form of the species. And therefore, Le Chatelier's principle, grab the less, even though it's a less favored component, the minor component in the equilibrium will grab that selectively and therefore drive the whole equilibrium from left to right. And so sodium hydroxide and sodium alkoxide are perfectly okay for many transformations that we'll encounter. So here's an example of a preparation, cyclohexanone with LDA, bang, enolate, okay? And you get the protonated amine base. So what do we do with these? Well, one of the beauty of these enolate anions is they act as carbanions. And carbanions, we know, or anions in general, can be potential nucleophiles. And indeed, this guy is a nucleophile, and it will react with carbon alkylating agents, preferentially at carbon. Even though we have two possible modes of attack, this is why it's called amidin, you can either attack at the carbon or at the oxygen. And it turns out that alkylations occur preferentially or exclusively at carbon. The reason for that is a little beyond this scope of this course, but let me put it this way. Part of bond formation bond formation involves the overlap of orbitals in the transition state, right? We've drawn a bunch of transition states in the SN2 reaction, for example. Well, this overlap is best if it's between atoms of the same element, because then the orbitals are very similar or the same in energy, very close in energy, in size. And so that maximizes the overlap integral between these species. So the difference between carbon and oxygen is quite substantial. Oxygen is more electronegative, all the orbitals are smaller. Okay? So that's one of the reasons. There are other reasons for this, but that's one of the reasons that I think it's readily understood why an alkylating agent attacks here. So here we have an allylic one that, remember, is more reactive in SN2 reactions, so I just threw that in order to remind you of that. You could have used propyl chloride or chloropropane. And out comes this product, pretty good deal. The alternative mode of attack, attacking an oxygen, occurs with other species that we won't cover, silicon-based materials and so on, and that would be irrelevant. One thing that one should bear in mind, though, is that protonation also occurs on oxygen. So if you take the enolate that you made by deprotonation and you dump in water, you quench it, basically, to make the corresponding alcohol, the enol. So kinetically, proton will home in on the oxygen. Again, because proton is now very small, most of the charge is on oxygen, and oxygen is smaller than carbon. So there again, it's in part an orbital matching scenario. But as we know, these guys are unstable, and they undergo proton tautomerization, meaning this proton migrates from this position over to here. We'll go into the mechanism of this in a second. And so, in essence, everything goes to carbon in the end. Okay? So in a way, this is irrelevant with respect to the outcome, but it's relevant. It should be in your mind, knowing that indeed the initial species here is the enol that then rearranges to the ketone. So kinetic product that then rearranges to the thermodynamic product. Now, when we do stoichiometric enolate formation on unsymmetrical systems, such as, for example, 2-methylcyclohexanone, then of course we have a choice of the left side and the right side. And fortunately, we can control that, because the more substituted side has, by default, protons that are more hindered. So they're more difficult to get at. And LDA is a sterically hindered base, and it clearly knows the difference between the two. So at low temperature, LDA will actually attack the less hindered proton to make this enolate selectively. Now, as it turns out, this enolate is thermodynamically unstable with respect to rearranging to the other enolate. So again, we have classic kinetic versus thermodynamic control. And so at higher temperatures, particularly in the presence of an acid catalyst, the less stable enolate will rearrange to the more stable enolate. Why is this more stable? Again, I hand wave. Literature says, and people, I'm not really sure about it, but literature invokes what we've invoked several times before, which seems to work. The more substitute, double bond, more stable. So if you just stick to that, that will help you remember this. Yeah? Fun? No. Oh. So we can actually control which side is then therefore deprotonate and which enolate you get. And this, of course, is significant with respect to controlling where your electrophile will go if your next step is an alkylation, such as methylate. Okay? If you hit this at low temperature with methyl iodide, it will give you methylation at this carbon here. So you get the dimethyl species, the 2,6-dimethylcyclohexanone. You get cis and trans, you get a mixture. If you get the more stable enolate, the thermodynamic enolate, then you will get 2,2-dimethylcyclohexanone. So that is useful. And it looks fine and dandy. We'll see in a minute that this isn't that there's a problem with the alkylation, but it works for some cases. So not only do we think about these enolate equilibria with acid base, where the carbonyl compound converts to the corresponding enolate, this happens even in the neutral. This proton tautomerization that we have typically always written as enol converting to carbonyl is a reversible equilibrium at room temperature. And so this equilibrium has been measured. For aldehydes, the equilibrium is a little better than for ketones. In both cases, the equilibrium is way to the left. So for aldehydes, it's about 10 to the minus 7. This proton shift, and this has been looked at quite carefully, needs a catalyst. So in solution, you either need acid or base to catalyze the tautomerization of this to that or that back to that. People have done experiments in the gas phase where there is no solvent and no external species, and the activation energy for the proton hopping from here back to here is enormous, 50 or 60, I can't remember the number, kilocalories per mole. I think it's in a margin entry in your book, in the new edition. So you need a catalyst, and the equilibrium way to the left, and this equilibrium constant actually translates into a delta G of around 9. Ketones are more stable, or the carbonyl function in ketones is more stable than in aldehydes, and so the equilibrium is even worse. So now it's 10 to the minus 9, and the delta G is about 11. Okay? Both of these numbers, however, are not prohibitive qualitatively with respect to the equilibrium being set up and reachable. Okay? So this is a fast scenario where this species is there. It's like this picture with the buckets. Okay? The bucket is quite a bit down here. The enol is the upper bucket. We have a connecting tube. Most of the water is down here, but the upper bucket is not as high that the rattling that occurs at room temperature isn't sufficiently strong, that water will splash and wet the upper bucket, so that there will always be a little bit of water in the upper bucket. And if you have a reagent that soaks up that water selectively, then all of the lower bucket will be emptied, essentially, by driving it off into a certain direction. So that's good to keep in mind. So what do I mean by room temperature? I mentioned this number before, very qualitatively, so that you have some ballpark figures in your head. It's 20 kcals. At room temperature, we have enough kinetic energy, the air floating around, bashing me as I speak. It's about 20 kcals. Okay? So this is actually way below that. So you can easily reach that at room temperature. Okay? So what is the mechanism in detail of the acid or base catalyzed tautomerization? It's trivial, really, but it does go through a stepwise process. With base, the enol, so we're looking just at the enol to keto tautomerization. Obviously, going from keto to enol is just the exact reverse. So with base, you deprotonate, that seems obvious, and then you get the enolate, two resonance forms, and then the protonated base reprotonates a carbon. And since this is more stable, left goes to right. With acid, the sequence of events is exactly the opposite. First, you protonate, and you protonate the double bond, like in the Markovnikov HCl addition. And this is completely regioselective. Protonation occurs only to the left, because the carbocation that you form is a hydroxycarbocation, resonance stabilized. So this is like super Markovnikov. Okay? And another thing, a hydroxycarbocation is the same, it's identical to a protonated carbonyl. That's the other resonance form. Okay? And so this just loses proton, and there you are. So it's a proton shuttle. You plug out the proton with the base catalyzed mechanism at one end and put it back at the other. And with the acid catalyzed mechanism, you add a proton at one end and take it away at the other. Okay? So it's a 1-2 punch, and the sequence of punches is left-right in one case and then right-left in the other. Okay? So how can we detect enolization? Most easily, this is done by NMR, actually, where you can actually demonstrate that there is a keto-enol equilibrium. Because when the keto form turns into the enol form, the proton out of the carbonyl has to come off. So if you dissolve your sample in an NMR tube containing deuterium oxide, then the proton will be exchanged for deuterium. If deuterium oxide is the solvent, the proton will just disappear in the ocean of deuterium. Meaning that as you mix, for example, 2-butanone with basic D2O, it deprotonates and then redeuteriates repeatedly over and over and over again until all alpha hydrogens have been removed. By NMR, you see this, there's a startling effect because proton NMR, you just look at the proton spectrum. Deuterium has an NMR, but it's millions of hertz away from the proton spectrum. So looking at the proton spectrum, the signals for these two blue guys just disappear. Okay? So that's a tremendous effect in your NMR. So that way you can easily tell whether you have enolizable protons in your sample and which signal corresponds to those protons, because you can make them disappear. More practical results, consequences, are stereochemistry. The fact that you can deprotonate here, and this can set up either an equilibration with enolates or just the enol itself, means that the carbon next to the carbonyl is stereochemically labile. And so one has to be careful with optically active ketones and aldehydes to not expose them to strong acid or strong base or at elevated temperatures, okay? Because then the stereochemistry will disappear, you get racemization. So in this case, if you start with S3-phenylbutanone and you dump in a little bit of base, and you deprotonate, you get the enolate is achiral. So you can now reprotonate at this carbon from down below, that gives you back there, but back this stuff, but if you come in from the top, you get the enantiomer. Okay? And so in this way, you just get a 50-50 mix of both enantiomers, i.e. racemate. Similarly, you can get stereoisomerization with respect to cis-trans or RR versus RS, diastereoisomerization, next to a carbonyl carbon. So that's easily shown in a cyclic system. You start with this cis compound and treat it with a little bit of base. This was done with KOH and ethanol. You deprotonate here, that makes the enolate. That kills the stereochemistry here. This one is still there, okay? But it kills it here. And so then reprotonation can occur from the top or from the bottom. Eventually, coming in from the top gives you an isomer that's more stable than coming in from the bottom, because this is cis and this is trans. And cis is more hindered than trans. Okay? So this converts completely to this side, over 95% to the more stable isomer. Okay, let's have a break.